This is us back when you were allowed to go outside and not have to social distance on a nice sunny day in Leeds. So looking forward to that again soon. There's a bit of previous work that we've done that makes us well placed for IoT projects in particular. One of the early ones was a project for Enterprise Car Club. So if you're not familiar with Enterprise Car Club, it's an app where you can book cars by the hour. So you run out, go up to a car, you can put in the amount of time you'd like to book it for, press unlock, and it actually unlocks the car remotely. You can open the glove box and there's some keys in there and you drive it around and drop it back off where you put it. There's some really interesting challenges around implementing this. We had to reverse engineer some APIs and get our hands messy with this one. This was for a company called City Car Club in Leeds, and they got bought by Enterprise. So we worked with them when we handed over the project, and they took it in-house, but it was a really good fun project to work on. And that's when we started sort of cutting our teeth with projects that meet the real world. We like it when it's not just like a web application, it's something a bit more real worldy, so you can, it has an actual physical impact. Another project we worked on was for British Airways. This was LED billboard project, basically a bespoke system to deliver video and collect different metrics and data. This was pretty fun for my colleagues who were trying to get a toolbox of spanners and screwdrivers through airports. That they're in first class lounges and also St Pancras, but we actually went and helped with the physical installation of these because this was way back when we were just sort of getting started with all this kind of stuff. And there's our client Gary up a cherry picker. Gary, if you're watching, got loads of pics of you getting all this set up. This is fun in St Pancras. So after doing these projects, we were getting a bit of a taste for this sort of real world meets digital sort of angle. And Lucy Zodian had got in touch with Ian Massing at Amazon. They put us in touch and they really wanted to know how they evolved their street lighting product. They've been doing street lighting for 60 years. Their technology is in most street lights. I think it's like 70–80% of street lights. They have some kind of technology in there. What we wanted to achieve was reducing the energy consumption was a big factor. Being able to report on any failures, things like day burners, so that's when lights are on during the day, and be able to sort of predict any sort of faults and failures. A common one we get is that the voltage level in a city or a particular street takes a big dip, and that can signal issues with transformers and things like that. So you can actually do proactive maintenance and go and repair this stuff. And then there's the sort of maintaining the software side of it. So we were looking at how we can actually update and add features to these things without going out with a cherry picker to each and every single one. So this is the system that we built for them. There's a trial running on the A64. So these lights are, there's basically a node that screws into the top of the luminaire, and they communicate with us over something called LoRaWAN, which is a long-range wide area network. It's a type of radio communication, essentially. We spent a lot of time developing an interface so you could group these. You can sort of group nodes together and sort of label them and things like that. One major part of the project was a profile builder. So if you wanted to build a profile that runs over time, you might have a trigger on and off point. So an on point might be when it gets dark below a certain level. So that's the lux on point. Or it might be a solar clock offset. For example, if you're in a tunnel or something like that, and you don't have access to daylight, so you might want it to be on a specific time relative to sunrise and sunset. Or it might be a school crossing light, and you want it to be on at a specific time, like 3:15 or something like that. You can set up all that in here and actually control the brightness. So for example, if a city wanted to save some money, they could at 3 a.m. when there isn't much traffic, they could be lowering the sort of luminaire output at that time. And we spent a lot of time trying to make this interface as intuitive as possible, because a lot of these things kind of looks like your sort of broadband router UI, and it's less than fun to use, and sort of explain how it works. Another thing we built was the ability to schedule these profiles. So it may be that you have a group of nodes that just want to be on over Christmas. So Christmas time, you have like Christmas lights or something like that. So you might choose your Christmas profile, grab the nodes, and then go into the calendar and assign it to that profile. It's also good for running trials for energy saving patterns. You can set a sort of standard calendar, or you can override it. Making sure that this interface was able to deal with lots of nodes at once is quite important. This is sort of building up a picture of what the network should look like in the cloud, but then you have to start thinking about, right, well, how do we get that information from the cloud to the nodes themselves? Fault data is reported upwards, so this is things like if the column's not vertical, if there's a power failure, if you're taking no measurement data. It's really important for sort of proactive maintenance. So all this data is sent over radio waves to a gateway. The gateway then relays this to our backend, and the backend then puts it into a time series database, so we can easily filter, query, run statistics and various models on it. And do whatever we need to do to figure out what the issues are. All these videos are available on the key.community website, which is a little website just talking about the product that Lucy Zodian have that we've developed with them. But yeah, I definitely recommend checking that out. Another issue they have was around commissioning. So instead of a sort of paper-based model, where you'd go out and when you're installing them, you write down what node you installed and where you put it, and if there was any problems, you actually do that through an app. So you can go around and scan them and plonk them in, and to let the app know where you put them. And then there's a whole automated commissioning process. So we built the app side of it as well. When we were designing this product, there were sort of 3 ways that we could have done it. So there's the first model, which is where you keep the nodes really dumb. They don't understand anything. They're just told when to come on and off. Keep the gateway really dumb and leave all the smarts in the cloud. For a lot of IoT applications, this is absolutely fine. If you're just taking sensor readings and it's just dumb data coming up and you aggregate it and run stats on it, that's absolutely fine. This doesn't really work for this application. The advantage is the node work, the firmware is really easy to write, but it adds a huge failure point. If we're telling the lights when to come on and off from the cloud, you have a problem where if there's a problem with connectivity, 3G, 4G connectivity between the gateway and the cloud, then you have an issue. If there's an issue with the cloud application, like somebody does a Friday commit and deploys something that, you know, that one line of code that you think is going to fix everything and it doesn't, that would cause a massive issue. Or other issues on IoT are, what if that 868 band that you're using gets saturated by a bad actor or another third party doing something we didn't expect? Another disadvantage is if we're sending data down, we'll hit this duty cycle quite quickly. So the duty cycle is, on the 868 band, you're only allowed to talk 1% of the time. This is to give other users the ability to use that frequency range at the same time. This is what I like to refer to as the pet net model. I don't know if anybody saw this on the Internet of Shit Twitter account, but I used to have one of these, and the servers went down and nobody's pets got fed, and that's a really, really bad idea. So the schedule lived in the cloud, and when it got round to feeding time, the cloud would send a packet down through your router to the device and trigger whatever it was in the device to sort of let food come out. That turns out to be really, really bad idea. And a lot of people were saying it's like starve your cat as a service. The second option is what some people may refer to as edge compute or fog these days, but it's moving some of that smarts closer to where the actual end IoT device is. So an advantage there is that the firmware is still quite easy to write. You can keep it quite dumb still. It defends against issues around 3G, 4G connectivity for the gateway side. The disadvantage is you still have issues around the 868 band, the LoRaWAN network. You still have duty cycle restrictions. You have to then actually write software for the gateway as well. If the gateway fails or crashes and the nodes won't react. So in a city street lighting application, this is still an unacceptable amount of risk. In the third model, and this is the most complex to implement, but actually the best solution overall. So the cloud keeps a full track of what the state of every node is, and it has full schedule data in the cloud, obviously, because that's where you prepare it effectively. And then the nodes get synced up with that state and actually run the schedule themselves. There's also lots of clever packet retrying and things like that that we've implemented within there. The advantage to this is if the LoRaWAN network's saturated, it still works. If the gateway goes down, it still works. If we hit a duty cycle, it still works. It moves some complexity into the firmware, so you have to write a bit more of that. And testing firmware can be more expensive in terms of time. So we've got a schedule in the cloud. We know what we want the nodes to do. How do we get it from the cloud down to the nodes themselves? So an example message might be something like 20 minutes before sunset, switch on. So how would we get that message down to a node? Now, if you're thinking about as a web developer or an application developer between machines, effectively, you might have some sort of JSON protocol, maybe. This is what that could look like. This is quite weighty. So instead of actually sending a full JSON payload like this, you would actually send binary instead. And there's a few different ways you can do that. So numbers in binary are typically between 4 or 8 bytes in length, and you define this ahead of time. This causes some problems, especially around IoT applications. One of the solutions you can use are protocol buffers and variable lengths. If you're designing a binary protocol yourself, good luck, have fun. It's what we did, but I wouldn't recommend it. Protocol buffers are Google's answer to this. Actually, when you visit google.com and you type a search, the machines talking to each other within Google's network all use protocol buffers to talk between each other. It's almost the best of both worlds of JSON and binary communication. The payload structure is agreed ahead of time, so all you're sending is the sort of values over the wire. So this is what a protobuffer file looks like. So you see there I'm defining that there is a schedule update, and it has a repeated number of time events within it, and a time event has an offset time, an offset type, and a brightness level. These numbers that you've put in the description file here are the order that they go in. So if you've ever designed a binary sort of format, like back in the old days when you used to have files that were designed to be loaded very, very efficiently and quickly into a computer, they were often stored sort of packed in, and often you'd have a number saying, right, this is the number of bytes that describes this thing coming up. So you'd have a 4 or 8 byte sort of integer describing how many more bytes there are to come in something. Unfortunately, with LoRaWAN, you've got about 50 bytes to play with, which is not a lot. So instead of saying, well, every number is going to be 4 bytes or 8 bytes, how about you say, well, we don't know how many bytes it's going to take, but we sacrifice 1 bit per byte in order to get that functionality. So the first bit of every byte is just answering the question, are there any more bytes in this number? And this means we can truncate any numbers that are small. Instead of using 4 bytes just to send the number 1, we can use just one single byte. Signed integers essentially chop the binary range in half and use the upper half for negatives. So this means that we then wouldn't be able to chop. You wouldn't be able to chop the maximum negative number for this number of bytes. So in this instance, you'd use a zigzag encoding. So 0 would be 0, -1 would be encoded as 1, 1 would be 2. So it sort of zigzags across, and as the number, either positive or negative, gets bigger, it sort of increases in value, and you're not then getting that completely all the ones for your largest negative number. And then this allows us to then use the variable length 7-bit encoding for negative numbers as well. It's very useful for things like offsets and things like that. I could talk all day about how we actually implemented it and how we did the over-the-air updates, but that's probably enough content in there for another 3 or 4 talks. Our results were great, so it's still early days, but Aberdeen are targeting 60% energy savings. So the vast majority of that, 40–50% or so, is through the actual switch to LED, and then you get your extra savings based on profile. So it's really important for them to be able to decide and manage and plan these profiles and send them out to the nodes. We also integrated with Alexon, so you effectively write your own energy bill based on the usage that you did. So if based on all the reporting and knowledge that we get from the nodes, we can actually tell them exactly how much energy we used and tell them that, and then that's how much councils get charged. So that's how you reduce your energy bill. The over-the-air update protocol that we designed is an absolute game changer, because it means we can add new features and roll them out. Previously, the cost of this was only calculated as a worst case, because you'd never want to do it and go out in a cherry picker and change every node. But the fact that you can do it over the air is an absolute game changer for them. Yeah, I just want to say thank you very much for listening to my talk. And yeah, if you have any questions, you can put them obviously in the Q&A or follow me on Twitter. There's also our website there, which is parallel.ax.